Good. All right then. So let's welcome group number 4 on LED. Some virtual applause.
Okay.
All right, over to you.
Yeah.
Okay. Good morning to... Hello. Boleh dengar?
Boleh.
Okay. Good morning to Dr. Zamir and everyone. We are from Group 4 and we are going to present about light emitting diode or LED. My name is Muhammad Luman Hakim and I will present the introduction of light emitting diode. Okay, first of all, what is light emitting diode? A light emitting diode, or LED, is a semiconductor light source that emits light when current flows through it. Electrons in the semiconductor recombine with electron holes, releasing energy in the form of photons. The color of the light corresponding to the energy of the photons is determined by the energy required for electrons to cross the band gap of the semiconductor. White light is obtained by using multiple semiconductors or a layer of light emitting phosphor on the semiconductor device. Okay, next we will continue with history of LED. It starts at 1907, where electroluminescence as a phenomenon was discovered in 1907 by the English experimenter H.J. Round of Marconi Labs using a crystal of silicon carbide and a cat's whisker detector. In 1927, Russian inventor Oleg Losev reported creation of the first LED in 1927. In 1936, Georges Distrow observed that electroluminescence could be produced when zinc sulfide powder is suspended in an insulator and an alternating electrical field is applied to it. While in 1939, Hungarian Zoltán Bay, together with György Szigeti, preempted LED lighting in Hungary in 1939 by patenting a lighting device based on silicon carbide. Next, Kurt Lehovet, Carl Accardo, and Edward Jamgotchian explained these first LEDs in 1951 using an apparatus employing silicon carbide crystals with a current source of a battery or a pulse generator and with a comparison to a variant pure crystal. In 1955, Robin Brownstein of the Radio Corporation of America reported an infrared emission from gallium arsenide and other semiconductor alloys. In 1957, Brownstein further demonstrated that the rudimentary devices could be used for non-radio communication across a short distance. In September 1961, while working at Texas Instruments in Dallas, Texas, James R. Baird and Gary Pittman discovered near-infrared 900 nanometer light emission from a tunnel diode they had constructed on a gallium arsenide substrate. By October 1961, they had demonstrated efficient light emission and a signal coupling between a gallium arsenide PN junction light emitter and an electrically isolated semiconductor photodetector. On August 8, 1962, Baird and Pittman filed a patent titled Semiconductor Radiant Diode based on their findings, which describe a zinc diffuse PN junction LED with a space cathode contact to allow for emission of infrared light under forward bias. In October 1962, Texas Instruments announced the first commercial LED product, which is the SNX 100, which employed a pure gallium arsenide crystal to emit an 890 nanometer light output. The first visible spectrum red LED was demonstrated by Nick Holonyak Jr. on October 9, 1962, while he was working for General Electric in Syracuse, New York. Holonyak and Bevacqua reported this LED in the journal Applied Physics Letters on December 1, 1962. M. George Crawford, a former graduate student of Holonyak, invented the first yellow LED and improved the brightness of red and red-orange LEDs by a factor of 10 in 1972. And last but not least, in 1976, T.P. Purcell designed the first high-brightness, high-efficiency LEDs for optical fiber telecommunications by inventing new semiconductor materials specifically adapted to optical fiber transmission wavelength. Okay, that's all from me.
Okay, I am ready. Okay, I will talk about device configuration. Okay, as like Lokman said before, LED is a semiconductor device that emit visible light when electric current pass through it. LED convert electric into light energy that are frequency used as a pillar light in electromagnetic application to indicate whether the circuit is closed or not. LED consists of chip of semiconductor material doped with impurity to create p-n junction that are the most important part in LED. This chip is located at the center of both, as you can see in the image below, and this chip contains two regions separated by a junction. The first region, which P region, is dominated by positive electric charge, where the second region, N region, is dominated by negative electric charge. The junction at the center is functioned as a barrier to the flow of electric between P and N junction. And as you can see in the left, it shows a simple LED circuit diagram. Simple circuit diagram is used for lower power indicate LED. Okay, LED will only turn on if the electric polarity is suitable. A large current flow when the voltage across the p-n junction is in the right direction, and it we call this device as a forward bias. The device also considered to be a reverse bias if the voltage is of the wrong polarity and a very little current will flow, so no light is emitted. And as you can see in the next slide, electron diffusion for the n-type side to the p-type side because the n-type region has high electric concentration and the p-type region has a high hole concentration. Similarly, hole transfer for the p-type side to the n-type side through the diffusion. If the electron and hole were not charged, the diffusion process will continue until concentration electron and hole on both sides were equal. However, in p-n junction, when the electron and hole move to the other side of the junction, they leave behind exposure charge on doped electron side, which are physically intercrystalline and unable to move. Okay, as you can see in the image, positive ion core are exposed on the n-type side, where negative ion core is on the p-type side. Between the positive ion core and the n-type material, between the positive ion core in the n-type material and the negative ion core in the p-type material, an electric field is formed. This region at the center of the image is called a diplicate region. Single the electric field quickly sweat free carrier out as the region is depleted of free carrier. When forward bias happen, the thickness depletion region is smaller that make easier atom to pass through. When reverse bias happen, the gap thickness in depleted region is become larger, so no carbon will flow. And we will talk about by Faris and Fahan.
Okay, so hi everyone. My name is Faris, and I'm going to continue with our operating principle. So we know that diode diode is an electrical component that only allows the current to flow in one direction. So we know that the electricity can only flow from anode to cathode, as we can see from the figure there. The anode anode for the LED is the long leg, while the cathode for LED is a short leg. So inside the LED, it's contained of two types semiconductor, which is N-type and also P-type semiconductor. So N-type semiconductor consists of electron, while the P-type semiconductor consists of holes. So as the electricity tries to flow from anode to cathode through the semiconductor materials, the holes and electron will react and begin to move toward each other when they interact with one another. So the energy is released. That energy release is in the form of light that we see when the LED is lights up. So let's see what is actually happened uh, inside the LED. So during the forward bias, so we know that forward bias condition is when the positive terminal voltage is connected to the P-type semiconductor, which is P-type semiconductor consists of holes that is positively charged ions, while the negative terminal voltage is connected to the N-type semiconductor that consists of electrons, which are negatively charged. So when the holes are injected by the positive terminal and migrated towards the negative side, while the electrons are injected from the by the negative terminal and begin to migrate to the positive side of to the positive side. So uh, why this uh, why this migration happen? So we know that in the forward bias condition, the depletion region in this forward bias condition is small. So when the depletion region is small, so the potential barrier in this forward bias is also reduced. So when the potential barrier in the forward bias is reduced, the electric field is now also reduced. So the electric field is now no longer held back the electrons and also holes in the p type and in the p-n region. Hence, there will be diffusion of current, diffusion of electrons and also holes. So hence, there will be current due to this flow of holes and also electrons. So in the second figure, during this process, holes and electrons will be recombined amongst them. So that means the free electrons from the conduction band will recombine with the empty holes in the valence band. So during this recombination, the electrons in the conduction band will jump to the valence band. So this jump of free electrons from conduction bands to valence bands, the electrons that jump will emit energy in the form of photon. So we know that the under the forward bias condition, the Fermi level energy for the P region is much lower compared to the Fermi level energy of N type in the N region. So uh, this allow the free electron from the conduction band to jump to the does this allow free electrons to jump from higher energy level in conduction band to the lower energy level in the valence band? So this different between two energy level, which is high energy level in the conduction band and lower energy level in the valence band, are called as a band gap or the forbidden gap. So this effect is called as electroluminescence that produce light in which we can see in LED when it lights up. So for LEDs, the silicon and germanium that we know is indirect band gap do not allow the light emission in the visible light spectrum because the wavelength is too low. Because in normal silicon and germanium semiconductor, this entire radiation of electromagnetic wave during recombination is in the form of infrared radiation. So as we can see in the figure there, the infrared wavelength is low, so that we can the the infrared are out of our visible light range, so that we cannot see it. So the infrared electromagnetic radiation is nothing but just heat. Thus, the LED is commonly made up by gallium arsenide, gallium phosphide, and etc. That we know this semiconductor is direct band gap. So we will go continue with Pak An.
Assalamualaikum and good morning. I am Muhammad Farhan bin Mustafa. I'm going to explain about reverse bias. A PN junction is said to be in reverse bias when the P-type is connected to the negative terminal and the P-type is connected to the negative terminal. When positive voltage is connected to the N-type region, the Fermi energy in the N-type is now lower than in the P-type region. And this is due to the free electrons in the N-type being attracted to the positive terminal of the supply voltage, which creates more positive ion in junction, thus broadening the depletion region. On the other hand, as the p-type is connected to the negative terminal, electrons are being injected into the p-type region, and these electrons are attracted to the positive potential of the n-type region and drifted to the junction and combined with holes adjacent to the layer of positive ions, which further widen the depletion region. And this resulted in increasing the potential barrier on the PN junction, making the energy required for charges to cross the depletion region even larger compared to zero bias PN junction. And the potential barrier continues to hold back electrons and holes, which resulted in minor charge flow and essentially assumed as no current flow, thus the LED does not light up. However, in reverse bias, a rapid rise in current can occur through junction breakdown. Initially, in the depletion region, thermally generated minority carriers in the neutral region can diffuse into the depleted region, which causes minor charge flow, and this charge flow is called reverse saturation current. Breakdown voltage is the particular voltage value where current increases rapidly, and this event is called the junction breakdown. Depending on the dopant concentration, there are two main mechanisms of junction breakdown, which is avalanche and Zener. At lower concentration, the breakdown is due to avalanche mechanism. The external reverse bias accelerated in the thermally generated, the external reverse bias accelerated the thermally generated electrons from p side to n side and the holes in n side to p side. The electrons can interact with the silicon atoms, and with enough energy, they can knock off the electrons from the silicon atoms. This process is called impact ionization and lead to large electron production, which give rapid rise to current. While at higher concentration, tunneling mechanisms take place due to the decrease of depletion width. Reverse bias causes an offset in the bands, which makes it possible for carriers to tunnel through the depletion region. And tunneling also leads to large increase in current.
Okay, Assalamualaikum. I'm Asnain and I will proceed with the advantages and application of the LED. So for the advantages of the LED, as we all know, it has a long light lifespan. Easily, the most significant advantage of LEDs when compared to traditional lighting solutions is the long lifespan. The average LED lasts 50,000 operating hours to 100,000 operating hours or more. That is 2 to 4 times as long as most fluorescent, metal halide, and even sodium vapor lights. It is more than 40 times as long as the average incandescent bulb. Less frequent replacement means two big things. lower maintenance costs in terms of labor, and lower cost for replacement parts because the bulbs simply do not fail for a long time. So the second advantage is the energy efficiency of the LEDs. LEDs generally consume very low amounts of power. The statistic to look for when we comparing the energy efficiency of different lighting solutions are called by one of two terms, luminous efficacy or useful lumens. These two items essentially describe the amount of light emitted per unit of power consumed by the bulb. So for the LEDs, the amount of light emitted per unit of power is higher compared to the normal bulb. Furthermore, for the normal bulb, they use the electrical energy to convert it to heat before convert it to the light energy. So this consumes a lot of energy, and they about 90% of the energy is converted to heat and only 10% converted to light. This is different to the LED. So the next advantage is the design flexibility. As the LEDs are so small, they can be used in virtually any application you can think of. They can be combined in bunches for a traditional bulb, used in isolation as a small device light, or strung out in sequence in a linear fashion. Just about everything you can think out can be done with LEDs. So the other advantages is the instantaneous turn on. LEDs can be turned on and off instantaneously. They will not have to warm up like the case of the metal halide lamps. Additionally, frequent switching doesn't cause degradation in this device. So this makes the LEDs the perfect device to be used as the indicator for various of purposes for various of devices. So next is they generate directional emission. The LED light only emits 180 degrees while the other light emits 360 degrees. As we all can imagine, the lights, the normal lights emits 360 degrees, and they will light up all their surroundings 360, right? So the light is emitted even to the ceilings, which you wouldn't want it as a lighting. So the LED solve the problem completely, and they give savings back in terms of the system overall energy efficiency. So last one is the zero UV emissions. LED emits the vast majority of the energy in the visible spectrum, a small amount in the infrared spectrum, and virtually none in the ultraviolet spectrum. This means that LEDs are able to safely reliably illuminate UV sensitive items like art that will break down and degrade over time if exposed to this type of emission. So LED can be simply categorized into three categories. They are used for indicators and display, lighting, and lastly the data communication and other type of signaling. So for the indicator and display, LED have a low energy consumption, low maintenance, and small in size, which led it to be useful as status indicators and displays on variety of equipments. They are used almost everywhere around us. The second is the lighting. LED are now commonly in all market from commercial to home use, standard lighting, stage theatrical, public installation, automotives, and wherever artificial light is needed. The last one is light can be used to transmit data and analog signals. LED are used to send data over many types of fiber optics cable. One of the example of the use of the LED as the light source for the multi-mode fiber optics cable. So let's take a look at the LED market growth. The global LED marketing size was valued at USD 50.91 billion into the 2020, and it is expected to witness a compound annual growth rate. The CAGR is the rate of the return for by the approximate time. So the CAGR for the global LED lighting market is 12.5% from 2021 to 2028. The global value for video walls market size stood at 15.9 billion in 2018 and is projected to reach 36.16 billion by 2026 with CAGR of 10.9%. Lastly, for the modular display, it is estimated at 5.49 billion in 2019 and is expected to grow at a compound annual growth rate of 13.2% from 2020 to 2027. So, which company is the leading company in the LED market? So, these are the some company that are leading in the market for the LED right now. So, the first one is Signify, or you all know as the Philips lighting before. Other is Samsung LED, Cree, Nichia, Osram, Seoul Semiconductor, Everlight, GE Lighting, and Sharp. Okay, I think that's all from us, and we'll proceed to the Q&A.
All right, thank you, Group 4. So let's continue with Q&A. Any questions from the floor? Anyone? Tak ada soalan?
Hello,
Yep. Go ahead. Siapa ni?
Izan.
Izan. Okay, go ahead, Izan.
Okay, how LED device can emit many colors?
Good question. How do they emit many colors? You mean at different time, right, Izan? One LED for color A, one LED for color B, right? Yeah?
Yes.
Okay then. Guys, Group 4. How do we get many colors? Anyone? You might. Yeah, okay, go ahead. Yep.
Okay, the different LED chip technology emit light in a specific region of the light of the visible light spectrum and produce different intensity. So which means they will gonna have the different intensity according to the visible light spectrum. So that's why it's gonna have the
what has to be different to begin with? How do you get say one is blue, one is green? So how do you get blue, and on the other hand you can get green as well?
The wavelength.
Yeah, go ahead.
The material
Okay.
used.
Okay, material used. Or do you want to elaborate on that? Material?
Using material that have various band gap, which can emit light in various wavelengths.
Okay, so okay.
And usually they just combine the three major colors to produce certain colors, such as blue.
Oh yeah. So for example,
yes.
what are those three colors?
I think it's blue, green, and blue, yellow, and red.
Yeah, is it to change the other colors?
Sorry?
Oh yeah. Do you mean the three colors again?
Oh, the three major colors, blue, yellow, and red.
Betul kah?
Not
Yellow is that. Yeah, we can search now and add on later on. We have a couple more questions here. So is in the band gap. What are the most common materials used for the LED? So that you can change color to here and there, different colors. What are some common semiconductor materials that we have in the industry?
For example, high intensity blue LED, we use gallium nitride.
Okay, all right. How about other colors? Can it also be used for other colors?
No, I think it's they use the different material.
All right, so I'll go to the chat box now. What is the most used LED device? I believe it's the material there. How can LED blinking, like lampu hari raya, baru raya kan? How do we get the blinking LED? Any ideas, anyone? Kenapa dia lit lap kan? You can even change the toggle button and get, different frequency and stuff. Any ideas?
Okay, about the blinking, lilat-lilat tu, Doctor. I think it use forward bias and reverse bias. So it have a two symbol LED.
Hmm?
It being at the same place. So just like what Pak An talk about how the material color blue green,
Hmm?
it use reverse bias and forward bias. So when the current is flow forward bias, it show it's like blue light, and when reverse bias happen at another side, it show red light. It's just
Okay,
like that.
so kalau let's say if you're using white light, for example,
Uh-huh.
okay, katalah well we have to define the blinking here. For example, if the blinking means on and off, kejap white light and suddenly there's no light. So is it due to forward and reverse bias as well?
Again, Doctor, about the question.
Okay. Well, we have to define the blinking. Blinking too means a lot, right? So one of the blinking types is on off. Well, we also have different blinking like different order of the LEDs kan. Banyak blinking lah you can define here. So if the blinking here means kejap on, kejap off, sometimes on, sometimes off, then what is happening inside? So that you can see the blinking on off.
What happened?
Any ideas?
Yeah, I think about it.
So it's like it's on for some times and it's off for some other times. Is it also due to forward bias for certain seconds and then no current passes through for another few more seconds so that it doesn't turn on? Anyone has any ideas or anyone in the group?
I think they use relay in the circuit to turn on and off for a sequence for the light.
Okay, relay. So that's another device. Relay. What is the function of the relay? Does it delay the sequence or something? Or that you read? So when you said relay, so is it like a switch or something?
Relay.
Ada belajar ke electronics 1 or 2?
Yeah, that I think it's like switch. It can be on and also off in the because when the relay coil has a power, so the switch will disconnect the power from the electromagnet and connect the power to the light bulb instead of it will light up. So when the relay no longer has power, it will switch back and turn off the power from the light bulb and give power back to the electromagnet again. So it's like switch, Doctor.
Okay, so that's probably one of the mechanisms that we have in the lampu raya. Well, you make it check it out later on. So next question is, what is the difference between LED and mini LED? Ni TV ni. And how can they be so small to fit in TV? Any ideas on the application? I think TV LED. So if you have read anything on this.
Ayu.
Ganas ni soalan ni from Amirul. You should have asked Amirul a lot last time. Okay, any ideas? Well, this is more towards application though.
Yeah.
Anything? Do you know anything on LED TV? And how do we fit LED in there? Anyone? Faris, have
We will
anything?
get back to you later, Doctor. Can I answer the Fatin Tahira question?
Okay, Fatin's question is, can you leave LED lights on all the time? Yeah, go ahead.
As Hasnain has talked just now, the LED can be turned on 24/7 because the LED is really conventional because it produce the minimal amount of heat, which is they unlikely to overheat or set to the fire. So that's why the LED can turn on 24/7. But in some scenario, the LED might be fail.
So, well, typically, okay, say if your house has some downlights, right? Downlight daripada ceiling tu kan. So usually how long do we replace? How frequent do you have to replace? Every few years? So that's pretty much the lifetime. If you have any idea berapa lama sekali kita berganti the downlight?
Tak agak lama.
How long? Like 2-3 years? Do you think? Every
I
2
think
years?
more than that.
More than that, yeah?
Yeah.
Okay. So, well, it boils down to the usage, by the way. If you, kalau sebelum ni kita tak study from home, work from home, mungkin siang tak ada orang kat rumah lah, for example, then the usage won't be so high. But if you're talking about the pandemic time where everyone is at home all the time, so the usage is way higher. Okay, way higher than it goes back to the, well, there's a parameter called lamp hours. Kalau dalam equipment pun, if you use LED, then it will state the lamp hours. How many hours have you used that particular light source before it goes out? Maknanya dia punya shelf life lah. Dia punya lifetime lah. Well, if you use frequently, then I would say 2-3 years. If you use sometimes, maybe it could last for 4-5 years. All right, another question here from Siti. I saw a few articles that LED light is good for growing plants, right? Another application here. Is it true? If yes, do the color of LED, does the color of the LED play any roles? Any ideas, guys? LED for plant growth. Horticulture, we call it horticulture. You've heard anything of that? If you like to share, horticulture, let me write it down here. Horticulture. Any ideas? Pernah terbaca?
Yes, I've heard. I've read about that. Just a little. Actually, yes,
Okay.
it does help during the growing of the plants. The plants actually reacts to certain wavelengths of light and certain color. So for mostly of the plants, they react to the red and blue, I think, for the LED for light.
Okay.
So they help the plants grow faster.
Right. So we also have this, for your information, we also have this project in School of Bio. Bio School USM. Ada project yang buat horticulture guna LED. Right. And this gives some ideas as well to what we call urban farming or vertical farming dalam building. So it's not only outside, the veggies, the plants, you can also grow the plants inside building where you can, allocate an area and put LED and see the growth rate is way higher if you compare to the plants without any illumination. So it works. Cumanya it's a matter of how much space do you have in order to do the project, okay? But it can be used because it responds to certain colors, certain wavelength, and it has to be related to the mechanism inside the plant, okay? Right, any other question? Yep. Sila. Soalan ke tu? Bukan? Okay, I have a question. I have not a question, I have questions. All right, okay. So you talk about white LED, right? How do we get white? We don't have any wavelength for white, isn't it?
We combine the colors.
Oh yeah, okay. So how do you combine the colors to get white?
What?
Well, you can search now and share. How do you get white? Maksudnya white yang kita tengok kat atas kepala saya. white.
Uh-huh.
So it's not from any white wavelength, right? There's no white wavelength to begin with, right? So what you see visible is a combination of colors from 400 to 700, the visible region. But
Mhm.
what are those colors to be able to get white? Or you started with some other color, one color, but you do something else? I heard about phosphor conversion just now. Did someone mention about phosphor conversion or coating, anything just now? I think in the first few slides, if I'm not mistaken, someone mentioned about phosphor conversion or something. Anything on phosphor conversion? I couldn't remember which one. I think in the first 5-6 slides, I couldn't remember which one. Anyone say anything on phosphor conversion or any other method to combine the colors to get the white light? Where's your slide on the white light just now? I think it should be there. Where white light or visible light or white light? Is it here? Next. I couldn't remember which one. Hold on. Is it here? The white light? Maybe not. Next. Hold on. Is it something related to the band gaps now? Faris mentioned silicon, germanium, but others visible light spectrum. I couldn't recall. I'll go for next slide. I remember I heard I heard phosphor or something as well. Well, that's anything? Or Farhan, how do we combine the colors? Okay, go ahead. What are the colors?
So just like before, we combine the major colors to produce white light, because from white light we derive to get more colors. So we combine them to get white light.
Okay, but I would like to know what are those colors?
Instead,
RGB.
Color
red, green,
is
and blue light.
green.
RGB, right?
Yes.
Yes, RGB.
Yeah, RGB. So the keyword is RGB, red, green, blue, with the right mixture. Do you know where's the wavelength of the white LED? Cuba tengok white LED punya wavelength. Well, we've been talking about wavelength, right? You said about radiative recombination, wavelength related photon energy and stuff. So to be able to get the white light, what are the wavelengths that you can see on the curve? Kalau tengok emission on the Y and wavelength on the X, dia mesti ada peak dekat certain wavelength to be able to give you white. You can search on the visible light or white light wavelength and try to see Google image. You definitely get to the wavelength.
About 400 to 530 nanometers.
Okay. So how many peaks do we have? 1 or 2 peaks?
2.
2.
Yeah, 2 peaks, right? So what are the exact peak wavelength? So you ada satu peak yang tinggi, one high peak, one low peak, right? One narrow and one broad,
Yes.
isn't it? So what is the peak wavelength? The exact peak wavelength for wavelength 1, wavelength 2? 400 watt and 500 watt. You tengok dekat dia punya peak. Okay, you have peak. So tengok dekat dia punya the apex. The peak of the wavelength tu dekat mana? 400 watt. Just now you said 2 peaks, right? So you go to the 2 peaks and see what are the peak wavelength. Tengok dekat x-axis dia, what are the values of the wavelength? Jadi you nampak dua wavelength kan? You see 2 wavelength, right?
Yes.
Okay, just mention the wavelength. It's broad, right? It's broad and coming to the yang tajam tu kan, kat atas kan, the peak, right? So look at the wavelength of the peak. The x-axis. What is the value of the x-axis of the peak?
450.
Yeah, 450, and the other one?
The other one is 550.
Yeah, 550 around there, right? So the first peak just now is narrower, isn't it?
Yes.
The narrow kan, the second one is broader, right?
Mhm.
And shorter than the first one, isn't it?
Yes.
Yes.
Tinggi, yang first one. So that's how you get the white light. So we learned about RGB now. So you learn about generation of light, RGB, combined in certain proportion, I would like to say, in order to get the white. And you have to be able to get your wavelength at 450 and 550, 540 more or less, to be able to get the white light on top of our head now. So that's how you generate white light. Okay, so nampak kan? Now you can relate, like generation of radiative recombination, the photon energy emitted, and then it has to be at a specific wavelength so that when they are mixed together, they give you white light. And we don't have any generation of white light. You have to go through something to be able to give you white. There's no white light original process. Okay. All right. My last question. Somebody else have any question? Ada? Tak ada? So someone mentioned about electroluminescence. Was it Faris or I couldn't remember which one? Faris, right? You said about electroluminescence, the principle
Yes, that's right.
LED. Okay, can you elaborate a little bit? What is electroluminescence? What do we do to get what do we want? We normally call it as EL, electroluminescence.
So the as we see from the figure there, so the electroluminescence is an optical phenomenon that happen to in the material to emit light when they have the electric field flow through it.
Okay, so you're supplying electric field in order to get the light.
Yes.
How do you get electric field?
So
What do you do to the device?
we connect with the power supply.
Simple answer, right? You just supply the current. Supply the current, and then as the output, you get the light. So kalau the opposite what you call? Opposite mechanism. Do you have any idea? What do you call that? Kalau you sekarang electroluminescence, you supply current, you get light. Kalau the opposite mechanism, any idea?
Photoluminescence.
Yes, photoluminescence. Photoluminescence apa? What do we get?
Electric.
Okay, right. So photoluminescence is the opposite behavior, right? Kita ada you tak pernah pakai kot PL dalam OLED, photoluminescence punya setup. Okay, so the opposite mechanism would be PL. So PL EL. Okay, PL EL, photoluminescence, electroluminescence. Yes, done. Thank you very much. So let us give a big round of applause to group number 4 on LED virtually. Right, thank you very much. It's 10:51. So we don't have time for another group. So tomorrow will be Wednesday. So we'll move on to group number 5 on laser diode tomorrow. Okay. Haziq, Hifzan, Rahimi, Sakina, and Shafika. Okay. So, all right. I'll see you tomorrow then. Bye-bye. Take care. Assalamualaikum. Good job, guys.
Waalaikumsalam. Thank you,
Thank you,
Doctor.
Doctor.
Assalamualaikum.
No worries. Bye. Salam.